Okay, so for this video we're going to do questions 17 through 22. Lots of math going on here. 17, compound contains only carbon, hydrogen, oxygen, approximately 48% carbon, 8% hydrogen, and the rest of the percentage, yep, that would be oxygen. So you have to infer that last little percentage that is oxygen. And it's just subtraction. So you could say 100 minus 48.38 and minus the 8.12, and you know the percentage of oxygen was 43.50% oxygen also. So you know the percentages, but how do you get an empirical formula out of these? There's a couple techniques. The one is, you have to assume the compound has some mass. Whether you want to assume it's 1 gram, 100 grams, 200 grams, you don't know. Pick a nice number. I always pick 100 grams. And the reason I pick 100 grams is so that this percentage, if I have a 100 gram sample and 48% of it's carbon, that means I have 48.38 grams of carbon if I had a 100 gram sample. And that would be 8.12 grams of hydrogen, and like I just said, 43.50 grams of oxygen. Grams aren't very useful in chemistry, so the general process is to convert these to moles. Hopefully it converts into nice whole numbers. There's 12 grams of carbon for every 1 mole of carbon. For every 1 mole of hydrogen, there is 1.007 grams of hydrogen. And then for every 1 mole of oxygen, there's 16 grams of oxygen. So let's just do that math there. 48.38 divided by 12.01. Hey, that's 4.028 moles of carbon. And this is 8.064 moles of hydrogen. And this is 2.718. Let's pause and check the math there for a second. Alright, didn't want to waste your time by just me tapping in my calculator, so I checked the math on all 3 of these, and they are correct. They don't come out really close to whole numbers. See, this one here, number 4.028, I mean, man, that's really close to 4. I mean, you get to the second decimal place, and then you hit a number, and it's a small number. 8.06, man, that's pretty small too. But this one here, 2.7, I'm not comfortable rounding the second decimal place, the second sig fig up. I mean, I have, how many sig? I have 3 sig figs here. I have 4 sig figs. Hopefully, the third sig fig would be the estimate. So if the third sig fig was the estimate here, this would be the number. It'd be a little bit flexible. That 1 might go up or down a couple. I'm not close enough. So what we do is we have a formula right now, but it's not a nice whole number. So we're going to guarantee a whole number by dividing each of these values by the same value. And what we generally did is we divided the smallest into the others, because that guarantees us one whole number. And that's right here. We're going to get a 1 for the oxygen. And then, let's see, 8.064 divided by 2.7. Oh, look at that. 2.966. That is just about 3. And then 4.028 divided by 2.718 again. Oh no, 1.48. That's still not great. So now we're going to multiply them all by some number to keep them really close to a whole number, so that the third sig fig is the only one we'd be estimating. Well, this I can multiply by any whole number. This one, I don't know. That one's really the key here. This is just about 1.5. If If I multiply it by 2, it should come out really close to 3. So let's see if I take that number and multiply it by 2, I would have 2.96, and that's my estimate, the 6. So that could be off a little bit. This one, 2.96 times 2, that comes out 5.9. And of course this one times 2 is 2. So that's where this answer came from. 2.96 is practically 3. 5.9 is practically 6. And what I mean is I'm only rounding one value, one decimal place up or down. Not a ton of values here being rounded. And then this is already 2, which is where that came from. For 18, essentially the exact same thing. There's 30% nitrogen and about, 69.6% oxygen. But you apply those percentages to the molar mass to convert it over to get the molecular formula. So this is the empirical formula. So you end up with an empirical formula, NO2, and it has a mass, the periodic table, that's 46 grams. Nitrogen plus 2 oxygens is 46. But then they tell us the molecule is 92, and the molecule should always be some multiple of it. And you look at 46 to 92, the molecule is twice the size, so it should have twice the formula. So N2O4, dinitrogen tetraoxide, is twice the formula, meaning every value in it, 2 times the nitrogen, 2 times the oxygen, to get from 46 to 92. Number 19, determine the molecular formulas given these empirical formulas. So you're just going to calculate the empirical formula and then see how many times it goes into that one. Let's try D. D is not hard to do at all. So we have sulfur, which is 32.06, plus the nitrogen, which is 14.007. So 32.06 plus 14.007 is 46. And then, so that's the empirical formula's mass. And if you take the molecular masses that are given and divide them by the empirical mass, so 184.32 divided by, this is the molecular mass, divided by the empirical mass, you see that the molecule in this case is 4 times heavier, which is why this is S4N4, because its mass is 4 times the empirical's mass. So going between molecular and empirical formulas can be determined by comparing the masses of the formulas. Number 20 is the balancing equations question. Just bounce back and forth on each side. E is more common in AP chemistry than the others, having to create the formulas before you can even balance them. So you have to do a lot of, barium's a +2, nitrates NO3 -1. So you have to make sure you get the right polyatomic ion. Ammonium, NH4 +1. Sulfate, SO4 -2. Sulfate's a -2 and nitrate's a +1. It's going to take 2 ammoniums. Let's see, barium sulfate. Barium's +1, sulfate, barium is a +2, sulfate's a -2, so that's why you only have 1 of each of them. And if you want to leave the parentheses around these polyatomic ions, that's okay, just make sure it's clear. And then after you have all the formulas built, you started with 2 ammoniums, but you only have 1 here. And you start with 2 nitrates, you only have 1 here. So that's why you have to put a 2 in front to balance it with the coefficients, and make sure that you don't lose nitrogen. Anytime you're balancing an equation, you're trying to make sure that you satisfy the law of conservation of matter or mass, really the same law, just from different perspectives. So we have a piece of matter called barium. We still have 1 piece. We have an ammonium. We still have ammonium. Or you could look at that as we have 2 nitrogens, and we still have 2 nitrogens. We have 8 hydrogens. 2 times 4 is 8 hydrogens. You could break it apart also. But really we're balanced equations so that atoms just don't go disappearing in reactions, because they can't. They have to be there. Number 21, what mass of ammonium perchlorate should be used in the fuel mixture for every kilogram of aluminum? So this question confuses people because there's no math in the initial question. So for every kilogram, so for every 1 kilogram, Promethean pen, there you go. For every 1 kilogram of aluminum, what mass of ammonium perchlorate should be used in the fuel mixture? So it's a stoichiometry problem. Pretty much have to set it up. You say, okay, I have 1 kilogram of aluminum. You could convert this to grams, but if you leave it in kilograms, your answer is going to come out in kilograms also. So I would just say for every 1 mole of aluminum, there's 26.98 grams. I really should have gone kilograms to grams, but my answer is going to come out in kilograms at the end if I leave this in kilograms. It should be aluminum, not silver. And then I go to my question. Let's see, there's 3 aluminums. Oh, that's a 1-to-1 ratio, a 3-to-3 ratio between there. So for every 3 moles of aluminum, there's 3 moles, it should be a 3 moles of ammonium perchlorate. And for every 1 mole of ammonium perchlorate, we should have the molar mass, which I can't do that in my head, and you know how to do molar masses. Now it's all set up and you can do the conversion, but this is really going to come out in kilograms because we didn't convert this. You know, if this is bothering you, so you could just change it right now. You could say, okay, 1,000 grams. For every 1,000 grams of aluminum, how many grams? You're going to get 4,400 grams of ammonium perchlorate if you do it that way. And that'd be fine. This doesn't specify what units to have the answer in. You could have grams, kilograms, as long as it's a unit of mass. If you change it to pounds or something like that, that would be wrong. It'd be completely wrong units. 22, same idea. It's just a stoichiometry problem. What mass of C6H8O7 should be used for every 100 milligrams? Convert it, don't convert it, leave it if you want to. What mass of CO2? Same idea, it's just a stoic problem. Just be careful that you run through the units correctly as you're going through the problem. Okay.